Okay, so today, right, will be the last class on this topic. Okay, and tomorrow we'll move to another module. Okay, which is on image transforms. Okay, so this topic is actually depth from defocus. Oh, just too wide. Still. Okay, it's called a DFD as opposed to shape from focus. This is somewhat like stereo. Okay, but then except that in the sense that you have to acquire a pair of images just like you do in stereo. But then the main sort of a difference is that you don't move the camera here. There is a Panasonic Lumix, some GH5 or GH6. Okay, that came out last year, I think 2018, I think. So that camera uses this. Okay, in order to do the hunting. So I thought we might as well look at it so that you'll at least know something about it, because they do mention that they're 100 times faster because of this. So I thought it's worthwhile spending a little bit of time. It won't take, but then for some approximate calculations like for hunting and all that, it's quite good. So and you'll see why. Okay, so the way this works is, okay, you have you have this kind of a 3D scene, right, and then you have a lens. Of course, this is all serial aperture camera, right, and you have an image plane. So what you do is you take one image. Okay, so actually you need a pair. Okay, it captures a pair of images. You can also capture more than two, but minimum two. Like I said, right, if you just capture one, then I think it's too hard. Of course, even though now deep learning techniques and all are there that do with just one image and so on, but those are all training based, So we don't want those kind of things now. So pair of images, and so captured and captured with rather different lens settings. Okay, lens settings. What that means is you might actually you might change this aperture of the lens, whatever, let's call this R. Okay, you might change the aperture of the lens. So that means you will capture one image with some lens setting, and then you capture a second image by changing the lens setting. You could vary one or more of these parameters. So one is R, another is this image plane to lens distance, but you don't move the lens, you just move the image plane. Okay, and I'm going to leave it to you to show that if you move the image plane, there's no parallax. Camera center doesn't move. You can move the image plane even if the scene is 3D. It's not a parallax. Okay, I leave it to you. Then what else can you? And then the focal length. Okay, so you can change one or more of these lens settings. It assumes that it knows them exactly, what these lens parameters are. Kind of assumes that all those are known. That's why I said it makes some assumptions that if those assumptions are valid, in the sense that, right, if you can satisfy those assumptions, then yes, then you can use this. But again, there are some other things, right, that I'll tell you. So what it does. It's again a very, very fast technique. It's again a parallel technique, just like your shape from focus, except that it can just work with a pair of images. So imagine that, right, you captured image number 1 here, right, and then you captured another image which is image number 2. So what has happened is, because the scene hasn't moved at all, right, and we haven't moved the camera, moved the lens, right, we haven't moved the lens or anything. If at all, we can change U, F or R. So therefore, what it means is that you get, let's say, some space variant blurred image depending upon what the 3D scene is like, and then again in the second one, right, you will get again another kind of space variantly blurred image depending upon what you do. For example, if you decrease R, then it means that your blur will uniformly go down all over the image, and if you whatever, right. So it's a function of what you do with these three things. You can just choose to vary just one or two or maybe all three. Okay, now the point is this, right. So now what it does is, right, tries to kind of compare these two images in order to be able to tell what is the depth, because the depth is still the same, because from here to here, right, if some point from the center is at a distance d, then it remains at d, because you're not moving the lens at all. So in the second image also it remains at d. So basically d is unchanged in both the images. And if you move the image plane, right, you can still do a compensation for that. Okay, because image plane, if you move this guy, right, in the sense that if you move this to the left or to the right, you can do that and then still have a compensation. in the sense that you can kind of align the two. See, the point is, okay, now what is kind of done is the following. So the assumption, right, that it makes is that blur is locally space invariant. The blur is locally space invariant. So this is like saying that, you know, overall, okay, it is space varying, so it is spatially varying. So if you kind of compute what is the kind of blur that you have here, maybe that's not the same as what you have here, that may not be the same as what you have here, but over a local region. Suppose I pick some kind of a patch, but these patches are typically small, okay, they are not typically more than 64 across 64. So over a 64 across 64 patch, for example, I'm saying this as an example, take a 64 across 64 patch, right, then you would actually assume that within this patch, right, the blur is kind of a constant, which may not be true, because, you know, it could be slowly varying, right, it may not actually be true, but that's an assumption that it makes, because it makes that assumption just to simplify matters, and you will see why. Another assumption, right, that it makes is the blur can be modeled as a Gaussian. Blur can be modeled, okay, which is also the reason why it says from defocus. The other one was from shape from focus, right? So in shape from focus, we never even modeled the blur or anything. We simply said, when does a point come in focus? We never worried about what might have been the shape of the PSF and all in the rest of the frames. We never. But here, okay, it does model blur. So it says blur can be modeled approximately. That's what it means. Okay, can be approximately modeled as a Gaussian, which again means that you could actually incur some kind of error because of these approximations, right, that you are making. But no, it turns out that you know, in spite of these approximations, right, there is still for certain applications it may still be quite useful. Okay, so the way it works is as follows. So if you kind of look at a patch here, let's call this as G1, and let's kind of look at the corresponding patch here, which is G2. Okay. Now what you do is, so if you look at G1, right, so you know that there must have been some underlying focused patch there which got blurred, right, because of the lens parameters, right. I mean, ideally there must have been something that was all focused, right, which would be a pinhole kind of an equivalent, right. We can think of some focus guy which we can't see, of course, but this focus guy is probably what was originally there, but then we can't see that at all because our lens is not able to bring this 3D scene into focus, and that's what we are in fact using as a cue to, you know, find the depth. So assume that right, there was, I mean, all over, right, this image, okay, if this guy was actually focused all over, then under this patch, right, you can assume that there was some F which got blurred by some, let's say, a PSF H1 to give you G1, and then when you change the lens parameters, it gave you something like an H2 which got convolved with F in order to give G2, because of this local space invariant assumption, okay, because of that assumption that we are making upfront. So what this means is that you can write this as H1 convolved with F1, and then you can write this G2 is, this is a very simple method, okay, G2 convolved with F2. So I thought that it shouldn't take too long to do this. So then if you kind of go to you know, if you compute a DFD or something, then you can look at something like G1 of, okay, you know, omega comma some nu, then let's say that is like H1 omega nu into F1 of omega nu. Well, initially we'll take a continuous kind of a case, okay, and then a discrete approximation is what you will typically implement. So G2 omega nu is then H2 of omega nu into F2 of omega nu. Oh, sorry, both is F, okay, sorry, this is not F1 F2, because the underlying patch is the same, no, can't write F1 F2. See, this guy is F, okay, see, this is F, and F blurred with H1 is G1, okay, so this is not F1 and F2, this is H1 convolved with F, H2 convolved with F, okay. So this is like F of omega this is like F of omega nu, and this is F of omega nu again, okay. So then it follows that you know, so you can kind of write again, okay, so G1 by G2, let's say, or we can write G1 omega nu is equal to H1 of omega nu, and then substitute for F of omega nu, which is like G2 of omega nu divided by H2 of omega nu. Now whenever you do a division, you let assume that this guy, right, is non-zero. because if it is 0 for some omega nu, then you can't strictly speaking divide. Okay, which is why I said that a continuous case, right, we will assume that it is a Gaussian. Therefore, if it's a Gaussian, then it is okay to kind of say divide, right? It goes to 0 only as omega tends to infinity. So it means that G1 of omega nu is equal to H1. So F is simply G2 by H2, or this is like H1 by H2, H1 omega nu by H2 omega nu, okay, into G2 omega nu. Okay. This is on okay, so we have something like this on the one hand, which comes from the intensity information, right? This is all the photometric information. So this is coming from the photometric information. We can simplify this further, but we'll come back to that in a minute. There's one more thing which is happening, which is like saying that since we are modeling, okay, H1 and H2, right? These are all being modeled as a Gaussian. So in each case, right, you have something like a sigma 1 parameter, and then for the other you have something like a sigma 2 parameter. So we know that sigma 1, right, is some rho. So let me write this as R1 U1 1 by omega D1 minus 1 by D. Okay. So that basically means omega D1 will again be something which gets automatically governed depending upon how you choose your focal length R and V or U. Okay, and then sigma 2, that means when you change the lens parameters, rho is a calibration constant, it's the same camera, rho can't change. So you have rho into R2 U2 1 by omega D2 minus 1 by D. Right, this will be the second equation, right? So one for the first sigma, another for the second sigma. This is all local. So the sigma 1 and sigma 2 could be varying all over the image. So you're sitting at one patch and you're sort of saying that this is the sigma that governs that patch. Okay, then what we can do is then we can write sigma 1 by rho R1 U1 is equal to 1 by, okay, or we can say minus of this plus of 1 by omega D1 is equal to 1 by D, and that is also equal to what is this, rho R2 U2 by omega D2. Wait a minute, let's pull this here. So minus of sigma 2, do the same thing, rho R2 U2 minus of this plus 1 by omega D2, right? And the main assumption that you are making is that the D is the same, okay, which is valid in this case because you have not moved the camera. Okay, so your D for that point, right? Only the amount of blur that point suffers on the image is changing, but the point itself is still the same in the scene. So which then means that you can maybe multiply. Okay, but let's do some rho R2 U2. You can do it in whichever way you want. So we can say from here, so we can say minus rho R2 U2 by rho R1 U1, okay, plus 1 by, or okay, plus 1 by omega D1 minus 1 by omega D2 into rho R2 U2. R2 U2 is equal to minus sigma 2, right? Or we can say sigma 2 is equal to, so this rho will cancel off, or we can say sigma is equal to rho into 1 by omega D1 minus 1 by omega D2 to R2 U2 plus, oh no, omega D2 minus D1 here. So I should write it as D2 minus omega D1. If I want to write everything as positive, then this is plus R2 U2 by R1 U1. So we can write this as alpha sigma 1. Okay, so suppose we call this is alpha. Let's call this is alpha. So alpha sigma 1 and then plus, let's say, beta, where we can say let's call this guy as beta. So this is beta. Let me just check if everything is okay. So sigma 2 is 1 by omega D2 rho R2 U2, okay, plus R2 U2 by R1 U1 sigma 1. Yeah, okay. So what this means is that that you have this purely from the lens parameters, right. So this is purely coming from lens parameters, because you change the lens parameters, you have one equation that actually that kind of say relates sigma 2 and sigma 1. Now let's kind of go to this one. Okay, G1 is equal to H1 by H2 times G2. Let's go to the photometric thing, which is the intensity. So what was it? So we had like G1 of omega nu is equal to H1 of omega nu by H2 of omega nu times G2 of omega nu. Okay, so then we know that H of omega nu is e power minus omega square plus nu square by 2, but then sigma square gets multiplied on top, right, when you take the Fourier, correct. I mean, if you have H of x y to be 1 by 2 pi sigma square e raised to minus x square plus y square by 2 sigma square, then when you take the Fourier transform, right, what is that? As long as you have this factor in, then it becomes e raised to minus of omega square plus nu square by 2 sigma square. So the sigma square comes on top, right, when you go to the Fourier domain, right. This is something that you all know. So this Gaussian is one of those special cases, where the shape is retained, right. When you go to the Fourier domain, the shape remains the same, still remains a Gaussian. So then this means that, right, this leads to e power minus of omega square plus nu square, and we can write this as sigma 1 square minus sigma 2 square into G2 of omega nu, right. Or we can say ln of G1 of omega nu by G2 of omega nu, okay, we'll bring this down, is equal to minus of omega square plus nu square, there should be a by 2, okay, square plus nu square by 2 into sigma 1 square minus sigma 2 square. Or in other words, you have sigma 1 square minus sigma 2 square is equal to minus of 2 by omega square plus nu square into ln of G1 omega nu by so you get an equation of the type. So now the point is this, right. So actually, okay, this is supposed to be valid for all omega nu, right. Of course, we may not take omega and nu both 0, because then it will blow up, but otherwise for all frequencies, right, it looks like there's only one value that you should ideally get, right. Whatever I do for any frequency, it looks like theoretically I should get only one value, but in practice, okay, there is something called leakage and all that. I don't want to go to that. So what is normally done is you take the average of this value on the right hand side, because this is available to you, no. See, you know the value, G1, G2, at what value of omega nu you are computing it. So the entire thing on the right hand side is known to you. So you can either compute the average, or you can compute the median. Okay, again, okay, it's up to you, average or median you can compute in order to get an estimate for sigma 1 square minus sigma, because actually this is a very simple thing, it should work for all omega nu, but then due to noise and other things, and there's something called leakage and all that, so you may just want to average. Now you have actually the other equation, right, where you had sigma 1 is equal to alpha, sigma 2 is equal to alpha sigma 1 plus beta, right, that's what you had, no. Yeah, alpha sigma 1 plus beta, where again, okay, here if you notice, okay, these things are all known, okay, we are assuming that the camera calibration, so if you look at beta, we assume that rho is known, omega, I mean, this is like only if these things are known, R2, U2, right, all these are related to lens. Similarly, R2, U2, R1, U1, these are all related to lens. So we are saying that alpha and beta, these should be known. Again, if you don't know, then of course you can't use such a method. So you are assuming that all these things are accessible, and you actually have these. I mean, you can gain access to these values. So in which case, right, you will actually end up with one equation which is coming from the lens, the other equation which is coming from the say photometric info, and then you can actually solve for sigma 1 and say sigma 1, or sigma 2 or both. And then once you know sigma 1 or sigma 2, right, then you can actually go back, and then if you know everything else, you can actually go to this equation, the first equation that you had, right, that was relating depth. And so you had this equation, so you can go to this equation, plug in the estimated sigma 1 or sigma 2, and then know all the lens parameters, plug them all in, and then that would give you an estimate of depth at that location. I mean, that will be the depth for the center of that patch, by the way. Okay, that will be the depth for the center of the patch. Then you have to kind of move this patch to the next pixel, okay, and then you kind of go on all over the image, right? And then but again, right, this can also be completely parallel, because you're not putting any constraint on adjacent depth value should come out to be similar or anything. If you don't put anything like that, then it can be very fast, but it can also be noisy. Now these guys, right, the Panasonic guys, what they've done is they've done something smart. So they know that depth from defocus is probably not the probably ideal thing to get a depth map, and they don't need a depth map. Depth map, by which we mean the entire scene, right? We want to know where is every point. That is not what is of interest to them. So what they've done is they've used it to actually do hunting. Right? So this hunting thing, so this is Panasonic, you can check this, okay? So now you should understand, if you go and look it up, Panasonic Lumix, I think it's called, okay? GH5 or 6, I do not know, okay, something. So this uses DFD, okay, to achieve 100% speed up over, let's say, existing speed up in hunting. So the hunting, right, I told you already, right? So this is something that it uses for autofocusing. So what it imagines is, right, so instead of capturing, like I said, normally typical cameras will capture about 50 to 100 frames and try to look for some contrast measure, which will tell, right, which lens setting is this thing coming into focus. Instead of working on that many images, what they do is they simply capture 2 images by changing the lens setting, and they assume that the center of the image is what is of probably interest to you. Naturally, right? That's what I said even in the last class. You may be interested in the center, and they assume that the central thing is probably one flat plane. It could be wrong. Okay, it could be that something is changing very drastically there, but these are all assumptions that they make. So what they are assuming is that right, that basically this patch is almost has one sort of a constant depth. Okay, and then what they do is they will actually use this DFD, right, and then because it's only 2 images now, and they will get an estimate of depth for that layer. So it's like a layered, you can think of the scene as being a layered scene, and you are interested in the middle guy, in the central portion of the image, and therefore for that, right, you find out a depth value, and once you know the depth value, you know that this need not be very accurate. So what they do is around that depth they capture. So now that they know where the scene is likely to come into focus, so around that, right, they just capture a few frames, 10 frames or something, and do a shape from focus. Not shape from focus, they do a contrast sort of a measure in order to then arrive at the actual lens settings. And this apparently, right, it's very quick, gives a 100%, a factor of 100, not 100%. It's a factor of 100. Achieve a factor of 100, not 100%. Okay, a factor of 100. 100%, I mean, we don't care. So speed up in hunting. Okay, so this I thought I'll just tell you because this is like stereo. I mean, and then afterwards, if you see the papers that are there, they kind of talk about stereo plus a defocus and all that, and then it all kind of, then it becomes very, very complicated. Right, you can have a lens, and then you can move the lens, then you say there is also defocusing effect, you change the lens parameters, you also translate the camera, so you have a stereo, you have a defocus cue, blur cue, can you combine both in order to come up with a kind of a better estimate. So right, those that do kind of research in these areas will try to think in those ways, right? How do you kind of expand the scope of this problem? Because to say that, right, a camera has to be exactly still there and not move, and then I should be able to change the lens settings may not be a practical thing. So they would assume that what if there is a small shake or something when you capture the second one? Can't assume that it will exactly be at that location, which means there will be a parallax. And then equivalently what will happen is your computation will go up. It will become a more complicated problem, but that is okay. I mean, if you want to write a paper, that's what you do. Right? You make a simple problem, make it kind of complicated, right? That's how you write papers. No, I mean, you do that provided, right, makes sense to do it. You don't write papers just because you have to write one. Okay, now the last thing, okay, that I wanted to talk about was, until now, okay, we have looked at what is called the optical blur. And now I want to ask you something. You've also seen motion blurred images, right? Assume that the camera by itself itself, right, is not really introducing any blur, in the sense that the optically, right, it is completely sharp. Okay, I have a camera which can capture all the scene completely sharp, but then when I actually capture something that is moving, okay, I see some kind of a smearing effect. Okay, that does not happen because of optical defocus. That happens because either the camera is moving, okay, or the, what do you say, okay, or you have a moving object. So let me write it down, right. So this motion blur, okay, what could be the likely causes? So one, camera motion. Again, it could be a complete 6D motion, okay, because this is not in the sense that all three rotations, all three translations is not under our control. So camera moves, but then scene is static. Okay, this is somewhat sort of doable. The sense that you assume that the scene is static, like for example this class, and then I take a camera and then for some reason my hands are not stable and there is a shake. Okay, so you will see that all over the image there will be some blurring, and again, right, depending upon what kind of motion I incur, my hands incur, the right, what you will see as blur will also change across the image. Okay, so scene is static, so camera motion can be kind of full blown, in the sense that three R's and 3 T's. Okay, 3 translations, 3 of these rotations. Then the second thing could be that object motion. Okay, need not be just one object, there could be kind of multiple objects. If there are multiple objects, then it makes it even more hard. But let's assume that there is object motion, but the camera is static. And then the third thing is both are moving, both camera and object are moving. Okay, which is even more hard, and object are moving. Now, what I kind of intend to show is, okay, so this is also another form of image formation, right? If I ask you, I mean, how do you think that image gets formed? Let's kind of say, look at the first case, which is just the camera motion, which is the simplest of all. Okay, how do you think that, just as right, when you have a lens, you can now right, think about how the image formation probably happens. Suppose I ask you the same question now with respect to motion blurred image. Somebody gives you a motion blurred image. How would you kind of interpret this now? Because there is no lens blur now. What would be your interpretation? And then we will see the math. The math is pretty straightforward. But let's just intuitively, how do you interpret? Because right, the scene is in focus, but because you moved, there is blur now. So how would you? Because if you can do this, okay, then it actually opens up interesting avenues. I'll talk to you.